Of all the careers in all the world that a person could aspire to, you ended up a professional space traveler. Tell me what it was that motivated you or inspired you to become an astronaut.
I vividly remember when I was 5 years old, I saw the Apollo 11 lunar landing. And that was the beginning of my strong desire to fly in space. But at the time, there was no Japanese astronaut, and I thought it was beyond my reach to be able to work in human space exploration. And after working as an aeronautical structural engineer, I saw an advertisement on the newspaper that the Japanese Space Agency was going to select a few astronauts to be sent to NASA to be qualified as mission specialist. And at the time, this strong desire, a strong longing for space flight came back to me, and I wanted to take on this challenge of my life, and applied for the selection, and luckily got selected.
Tell me about the place where you grew up, Saitama?
Yes.
Is that pronounced correctly? Tell me about what that place was like when you were a boy there.
Saitama, like many towns nearby Tokyo, it is kind of like a combination of small town Japan and Tokyo suburb. And because of its location, which is in the vicinity of Tokyo, Saitama allows people to commute into the capital of Japan while living in a less crowded area. And there are a lot of favorite places, but my most favorite place in Saitama is Hikawa Shrine, which is said to be more than 2,000 years old. And it has nearby beautiful ponds and a beautiful park. And it is kind of like a quiet island in the bustling city of Saitama.
Is Saitama is it similar to growing up in the suburbs of Houston, shall we say?
Of course, Houston provides more spaciousness feeling to me compared to any part of Japan. But in a sense, it is like that. It's a suburban area of a big city of Tokyo.
Do you have a sense of how that place and the people that were there helped influence you become the person that you are today?
Yes, my parents, my teachers, my friends all influenced me a lot. And my brother and I grew up in Saitama and under the watchful eyes of our very caring parents, and our teachers always encouraged me to have strong dream and work hard. And I really thank them for doing that, and they set the foundation of who I am right now.
When you flew space before, did you get a chance to see Saitama from orbit?
Yes, very much, but you have to be very careful because the space shuttle flies at 17,500 miles per hour unless I'm watching on the computer display that shows where I'm flying. Of course, Japan is a small country. We just passed by that small island really quickly, but I took a lot of pictures when I flew in space. And as a matter of fact, on my second flight, students of my elementary school, they sang a song of a very famous Japanese song, and they gave a CD to me, and then I had an opportunity to listen to the wonderful singing of my elementary school pupil while I was watching the beautiful Japanese islands.
You mentioned that you became interested in flying in space as a child and didn't get a chance to apply until you were already an adult. Help me fill in the space in between. Tell me about the course of your education and your professional career before you became an astronaut.
After graduating from high school, Urawa High School in Saitama, I studied aeronautical engineering as an undergraduate and also as graduate. And later I received a PhD in aerospace engineering. And before I was selected as an astronaut, I worked as a structural engineer for Japan Airlines. And all my life, I was really interested in airplanes, and this fascination in flying, fascination with the flying vehicle, and the drive to take on challenge. Those things made me apply for the astronaut, and I was just lucky to be selected.
Well, as you say, you were interested in flying in space, but didn't think it was possible. What was it, do you think, that set you on the course of studying engineering and aeronautics?
Since my childhood, I was always interested in airplanes, and I was really intrigued why such a heavy metal thing could fly airborne. And I always made model airplanes, and someday I wanted to build an airplane by myself. And that's why I studied math and science and tried to learn English, because many of the technical books in aerospace engineering were written in English back in those days. And I was lucky to be able to pursue a study in that field.
Now, we know that flying in space can be something that can be dangerous. What is it that you think we get as a result of flying people in space that makes that risk one that you're willing to take?
I think by exploring space, we obtain new knowledge and new technologies that can benefit humankind of the entire universe of the planet. And not only that, by exploring our frontier in space, we will come up with new technologies that will allow us to survive as species in the future eternally. And what we are doing right now is a preparation stage to be able to survive as a species in the future. Someday we may need to go into space and live other planets to sustain our existence as a species. And also, in case of a lot of emergencies like tsunami, earthquakes, environmental change, what we are having now, what we are now gaining in human space exploration, the new technologies, for example, environmental control and life support system, those technology will help us to cope with this kind of difficulties that could possibly happen in the future. So I think the risks associated with human space flight is worth taking, considering all these benefits that we can gain from it.
You're a flight engineer on Expedition 18 and 19 to the International Space Station. Koichi, would you summarize the goals of your flight and what your main responsibilities are going to be?
On both of the expeditions, Expedition 18 and 19, I will serve as a flight engineer. And on the upcoming mission on the Space Shuttle Discovery on STS-119, as well as on my coming down flight on STS-127, I will serve as a mission specialist, and we'll be involved in the assembly of the International Space Station.
Give me a sense of what a flight engineer does on an International Space Station crew.
On board the International Space Station, currently we have 3 crew members on board, Commander Mike Fink, Flight Engineer Yuri Lonchikov, and Sandy Magnus. So 3 of them are conducting a variety of experiments and performing maintenance tasks to keep the system going on the International Space Station. When I go up on STS-119, I will replace Sandy Magnus and continue to perform a lot of experiments and the maintenance tasks of the International Space Station.
Now, you've flown in space before. You've flown to the International Space Station before, but never on an extended mission such as you're doing now. What are you looking forward to about the prospect of spending months off of the planet?
Yeah, I was very fortunate to be able to fly with my wonderful crewmates on SS-72 and 92. And both of the flights were less than 2 weeks long. And this time, I think my entire flight is a combination of two 100-meter sprint and also one marathon. And of course, the two shuttle missions are those sprints, and expedition station, long-duration flight, is the marathon part. And if you consider the shuttle flight as a kind of short-term TDY to a foreign country, I think long-duration flight is almost like a permanent assignment to a foreign country. So I'm very much looking forward to this. For me, it is a new challenge to live and work in the space station.
When you do, you're going to be Japan's first ever long-duration space traveler. Talk about the significance of your flight as it relates to Japan's space exploration effort.
It is over 20 years since Japan started this endeavor in participating in the International Space Station program. And early this year, two shuttle missions assembled the two components of the Kibo module on board the International Space Station. And time is now for us to utilize the wonderful experiment platform, the Kibo module. And to be able to conduct a variety of experiments, we need to be able to stay on board the space station on a long-duration basis to fully utilize the asset. And I'm very fortunate to be able to participate in the long-duration flight to fully utilize the Kibo module.
Do you have a sense of what do you think you're going to be able to accomplish, and you and your successors will be able to accomplish using Kibo on orbit?
Right. Kibo is the first Japanese spacecraft which can host a variety of experiments and on which the astronauts can live and work on a long period of time. And I think Kibo is a very important step for Japan to expand our frontier in space, because this is the first human space experiment module for Japan. And I am very thrilled to be part of this endeavor. And then for Japan, we will be able to gain a lot of experiment data and also experiences of living on the low Earth orbit for a long time.
Let's talk about your flight. Starts with, as you mentioned, shuttle mission STS-119. What are the goals of that mission to the International Space Station?
The STS-119 is going to launch the last thrust segment of the International Space Station. That thrust segment is called the S6 thrust, which houses two solar arrays. And those solar arrays provide electricity to continue a variety of experiments on the International Space Station. And we will have 4 spacewalks to put together the components on the S6 thrust. John Phillips and I will be involved in the operation of the Canadarm2 to install the S6 thrust. And it is a coincidence for me that I was also involved in the assembly of the first thrust segment of the International Space Station, Z1 thrust, back in 2000 on STS-92. S6 is the last component of the thrust segment of the International Space Station. I'm very lucky to be able to serve on both of those flights.
Is the addition of that final set of U.S. solar array wings, the S6 truss, is that contingent on the status of the starboard side solar alpha rotary joint?
The answer is no. The current status of the starboard solar array alpha joint allows us to install the S6 truss to the starboard side. And the previous mission, STS-126, performed the maintenance tasks such as replacement of the trundle bearing assemblies. They did the maintenance successfully, so we can continue to build the new element, the S6 truss, to the starboard side.
You touched on the fact that you're going to be involved in working the space station's robotic arm during installation of the S6 truss. Tell me more about what you're going to be doing during that joint docked operations on STS-119.
Yes, so using the Canadarm2 together with my crewmate John Phillips, I will be involved in the assembly or putting together or putting the component S6 truss to the S5 truss. And first we have to unberth the S6 truss. And John Phillips and actually Sandy Magnus will be involved in that. And after overnight park of the truss, this time John Phillips and I will be operating the Canadarm2 to install that big 32,000-pound component to the edge of the starboard side.
That'll be a little different than installing the Z1 truss.
Yeah, Z1 was 18,000 pounds, and this time it's 32,000 pounds, so it's almost twice as big.
And not just in terms of weight, in terms of other dimension of length.
Right, and of course it is a very long component. And so last time when I installed the Z1 truss, I was using the Canadarm on the space shuttle. And this time it's going to be my first experience to operate the Canadarm to the big space station robotic arm. So I'm very much looking forward to it.
In order to complete this task, does the arm have to ride out on the truss segment, or is it all done from one operating base?
Operating base is the same. Actually, the operating base will be different. First, when we unberth the S6 truss, it's from one location, and then we have to hand it over that S6 truss to the shuttle robotic arm, and then we move the base of the Canadarm2 so that we can reach at the tip of the starboard side of the truss. And then, again, we will take the S6 truss from the shuttle arm to the big arm, and then we install the S6 truss using the big arm, the Canadarm2.
So your operations are not just moving something around on the end of the arm, it's moving the arm itself.
Actually, moving the arm from the base, the mobile transporter will move the base of the Canadarm2.
Okay. Otherwise, what are your jobs going to be during that handover time on STS-119?
Yeah, of course. As soon as my seat liner of the Soyuz spacecraft is moved from the shuttle side to the station and to the Soyuz spacecraft, I will become officially the crew member of the STS Expedition 18, replacing Sandy Magnus. So I'll be busy transferring the items that I need to stay on board the International Space Station, starting with the seat liner.
And everything else you're bringing with you.
Yes.
Once the shuttle goes home, you're going to be spending time with Mike Fink and Yuri Lonchikov getting the station ready to handle a larger permanent crew. Give me some sense of what it is that's required on board the station in order to get the station set up to accommodate a crew of 6 people.
Yes, my crewmates of Expedition 18, Commander Mike Fink, Flight Engineer Yuri Lonchikov, and Sandy Magnus, they already started to set up the station to accommodate 6 crew members in the upcoming missions. And we need to have a new capability to host more than 3 people on board the International Space Station. And those systems are the water recovery system and waste and hygiene compartment, and also advanced resistive exercise device. For example, the water recovery system is a system that will make the potable water from urine and also the condensate water. And waste and hygiene compartment is a new toilet. And of course, we need to be able to perform exercise throughout the mission on a long duration basis. So those new equipments are very critical for the 6 crew members to live and work in the space station.
And as you said, most of that equipment was delivered on STS-126, but after you arrive, you'll still be doing work getting everything set up, correct?
Right. We need to make sure that these systems, for example, water recovery system, works appropriately for a long duration basis. And we will be, for example, STS-119 crew will be utilizing the new toilet on the International Space Station so that it can process the required amount to cope with the 6 crew members on the International Space Station. So we will be checking out new systems throughout the Expedition 18 and 19 before the second Soyuz comes up to house 6 crew members.
Another one of your jobs after you arrive is going to be preparing Kibo to receive its final components. Tell me about the Japan Experiment Module Exposed Facility and the Logistics Module Exposed section, and what you're going to be doing to get the station ready for them to be delivered.
On STS-123 and on STS-124, my Japanese colleague astronauts Takao Doi and Aki Hoshide, they participated in assembly of the International Space Station's Kibo module. And on those missions, they installed a logistics module and also the pressurized module, which is a core component of the Kibo module. On STS-127, which is the last flight to assemble the Kibo module, the crew will bring up two components, exposed facility and also the logistics pallet. And I will be involved in the robotics operation to install the exposed facility to the Kibo's pressurized module. And after that, I will also be part of the robotics operation crew to install the experimental logistics module exposed section to the exposed facility. On that pallet, there are 3 payloads. And those 3 payloads will be transferred from the pallet to the exposed facility using the Kibo's robotic arm. And I will be involved in that robotic arm operation as well.
And that's all, as you say, during STS-127.
Yes.
Is there work before 127 arrives in order to get Kibo on orbit ready to accept these new components?
Yes, STS-124 crew members, Karen Nyberg and Aki Hoshide, they performed the checkout, and also Greg Shamitov and Sandy Magnus are part of the checkout crew members of the Kibo's robotic arm. But what I'll be doing during my Expedition 18 time is to have the final checkout of the Kibo's robotic arm by demonstrating the very similar trajectory of the motion of the arm during the STS-127. Those trajectories are the trajectories for the transfer of the payloads to the exposed facility. And after that is completed, we will be ready to use the Kibo's robotic arm for the first time operationally.
Kibo is Japan's first manned space facility. How are the people in Japan responding to the flight of the Japanese components and the Japanese astronauts to the space station and the start of operations in Kibo?
Yeah, when STS-123 and STS-124 missions delivered the first 2 components of the Kibo module to the ISS, we had a very big media coverage of those missions, and it created a very big enthusiasm among the people in Japan in human space exploration. And it's over 20 years since Japan started to work on this project, and I think taxpayers, they deserve to see us get to the next level, which is the utilization of the International Space Station. Each time when a Japanese astronaut flies in space, the media coverage is very big, and I hope my flight as a long-duration flight crew member will further motivate the people in Japan in human space exploration.
Well, let's talk about science. A lot of the science that is done on board the station is research into how people can live and work for long periods of time in a microgravity environment. Tell me about some of those kinds of experiments that you'll be working on during Expeditions 18 and 19.
Okay, one of the experiments that I'll be involved in human physiology is as a test subject, I'll be participating in an experiment using a bisphosphonate, which is on the ground, we use the bisphosphonate as a medication, which is a countermeasure to osteoporosis. In space, we have a very similar phenomenon of losing bone density, which happens to both men and women, young and elder. And as a test subject, I'll be testing the bisphosphonate, the medication, to see if that has any influence not only on the osteoporosis on the ground, but also for our bone loss in microgravity. Mechanism is different, but if that helps to alleviate the bone density loss, that would be very important data for us to continue our flight to Mars, for example. And that's one example. And for example, in fluid science, I'll be involved in a variety of experiments, and one of the examples is ice crystal growth experiment, which is a JAXA experiment. And in that experiment, utilizing the fluid test rack in the JAM module, the investigators will be checking the ice crystal formation in microgravity. And that kind of information or the data will help us understand a variety of phenomena happening not only on the Earth, but also in the different planets of the solar system. And also as an European Space Agency experiment, I'll be involved in a test or experiment called the GeoFlow, which simulates like a mini core of the Earth cores. The Earth core, for example, the inner core is solid and made of iron, and the outer core is liquid and it's made of nickel iron. And the outer core actually has a temperature of between 5,000 to 6,000 Celsius, degrees Celsius. And because of this temperature gradation, it creates some sort of motion of the outer core liquid. And it is believed that this motion of this electromagnetic substance causes this Earth magnetism. So by having a simulated Earth core, inner and out core, in an experiment module, they can study the actual phenomenon or what's happening in this fluid that is simulating the Earth core. And that's one of the examples of experiments that I'll be involved in.
All of these kinds of different scientific disciplines, research is going to be able to be done inside Kibo. There's that many different facilities. Actually,
the GeoFlow is in the Columbus module, and ice crystal experiment is in the Kibo module. And for Kibo module's experiment, I will also be part of the experiment called Dome Gene, which is to study the influence of microgravity in the cell differentiation and morphogenesis of a cultured cell of an amphibian. And we have CyberRack to conduct the experiment. And the experiment itself is going to go up on STS-119, and I'll be involved in that experiment throughout the long duration flight.
Kibo does have facilities to support experiments in quite a range of disciplines.
Right, life science, fluid dynamics, material processing, and there are more experiments coming in. And what I talked about is the inside of the Kibo module, the core module, JPM, and after STS-127, we will have experiments on the exposed facility, which I will not be involved during my flight, but there are more capabilities added on to the Kibo module.
There's something else that I don't think you will be involved in, but I want to ask you about it because 2009 also promises to see the first launch of the Japanese cargo vehicle, the HTV, to the International Space Station. Tell me about that spacecraft and about how it will contribute to space station operations.
Yeah, HTV is also has also been in the works for the JAXA, the Japan Aerospace Exploration Agency. And HTV, or H2 Transfer Vehicle, is a logistics supply vehicle to the International Space Station.
And just so people understand, H2 is?
Right. Yeah, H2 is a Japanese rocket developed by JAXA, and we are currently developing the beefed up, the more powerful version, which is called H2B. And that will carry the HTV to the International Space Station. And that will be launched from Tanegashima Space Center that is located in southern part of Japan. And after launch on the H2B rocket, it will perform automatic rendezvous to the International Space Station. And once it's approached to the International Space Station's R-bar, it goes up gradually until at a distance where astronauts on board the space station can use the Canadarm2 to grapple the HTV. And HTV can carry not only the supplies and experiments to the interior of the International Space Station, but also it can carry external items. Could be bigger items like batteries outside of the space station. So because of this logistics supply capability, HTV will play an important role, especially after the retirement of the space shuttle, because currently only the space shuttle can carry those external payloads like batteries.
The HTV will carry those payloads inside it, but they will be deployed outside the station.
Actually, HTV itself has two major sections. One is the interior portion of the HTV, and also there's an exposed pallet as well. And the exposed pallet itself can carry, for example, GEM, the Kibo module experiments, or the USOS batteries. So we need to use the Canadarm2 to take out the exposed pallet from the HTV vehicle, and then either put it on the mobile-based system or to the Japanese module's exposed facility. And after that, we will either use the Japanese robotic arm or the Canadarm, and also special purpose Texas manipulator could be used to further deploy the individual batteries to be housed to the International Space Station.
So the HTV is more flexible in the terms of the kinds of cargo that it can carry than the shuttle or Progress.
That's right. So this uniqueness of the HTV is, I think, the capability to carry the external payloads.
Your mission is going to stretch from Expedition 18 into Expedition 19 at the time when Gennady Padalka and Mike Barrett arrive in the Soyuz in March. How's it been for you to train with not only 2 station crews, but 2 shuttle crews?
Yes, it's in my previous flights, I only worked with 1 crew at a time, so which is a very new thing for me. But I think the more the merrier, and I am so glad to be able to work with 4 different crews, STS-119, STS-127, Expedition 18, and Expedition 19. And from the very beginning of training, I felt that I was perfectly integrated into the crew. And this open mind and open dialogue really made this experience for me very positive.
Once you become a part of the Expedition 19 crew, you'll be doing the same sorts of tasks as you were as a member of the Expedition 18 crew.
Right. But when Gennady and Mike Barrett arrive on the Soyuz spacecraft in March, I would be already there for about a month. So I hope the transition from Expedition 18 to 19 could be smooth, and I need to make sure that it's going to happen.
And then your ride home is the next space shuttle that visits, STS-127. Talk about the goals of that part of your mission and the tasks you'll be working on during STS-127.
STS-127, also known as ISS Flight 2JA, is the last of the 3 shuttle missions to assemble the Kibo module. So for Japan, it's a very important mission to complete the assembly of the Kibo module on the ISS. And there are 2 components that we brought up on the OV-105, this endeavor on the flight. Those are the exposed facility of Kibo module and also exposed logistics pallet that will carry 3 different payloads. And together with the crew, commanded by Mark Polanski, I'll be involved in the robotics operation of the assembly of the final components of the Kibo.
You're going to be there over a period where the Japanese sections of the space station are really going to be completed and be up and running 100%.
Right. So I'm very fortunate, and I feel just lucky to be able to serve as a crew member to complete the assembly of the International Space Station. When I became an astronaut 16 years ago, I always dreamed of working on the assembly of the Kibo module and staying aboard the International Space Station. So for me, this is really a dream come true.
Of course, all of the nations that are building and operating the International Space Station have exploration plans that go beyond this particular vehicle. Koichi, what is your philosophy about the future of human exploration of space and the contribution that the International Space Station is going to make to that future?
I think for us to expand our frontiers in space, international cooperation is essential. And this ISS project has demonstrated that it's possible. But it was not easy. We had to overcome so many challenges to be able to work together as the partners of the International Space Station. And I think future human space exploration will depend on the results of this International Space Station. And I think we have established a firm foundation of international cooperation in human space exploration. And this is the way that we should continue in our searching for